When we try to understand the environmental state of the planet, we rely on authoritative sources like USDA surveys and NASA satellite imagery. These datasets are rigorous, but they operate on institutional cycles, measured in months, sometimes years. The reality on the ground does not wait for a quarterly report. Soil moisture depletes in days, pest pressures emerge overnight. Climate adaptation happens in real time, and it is largely invisible to orbital sensors passing overhead once a week. Closing this temporal gap typically means deploying massive, expensive arrays of hardware, weather stations, soil probes, and new satellite constellations. LeafEngines takes a different architectural approach. It closes the gap without deploying a single new piece of hardware. It treats the active, daily inquiries of people working the land as a continuous data stream, complementing static orbital models with real-time human intelligence. The architecture relies on the existing infrastructure of Telegram. By tapping into a platform with 1 billion users, LeafEngines bypasses traditional software deployment friction. There are no App Store approvals, no SDKs to integrate, and no procurement cycles. The tool is instantly accessible in over 50 countries, specifically in agriculture-heavy regions where complex digital extension services are rarely deployed. A farmer simply opens a chat and asks a question about local soil pH, or uploads a photo of a struggling crop. They are seeking immediate assistance, but structurally they are pinging the system with highly specific geographic and environmental data. By capturing these natural interactions, LeafEngines begins the process of translating conversational text into a distributed set of environmental signals. When a user types a simple command like /soil, the ingestion layer strips away the conversational wrapper. The system extracts exactly 3 things: a set of GPS coordinates, a timestamp, and a structured text vector of the user's concern. The chat interface is merely a delivery mechanism, immediately discarded. What remains is a perfectly structured data point ready for institutional analysis. Because this ingestion requires almost zero bandwidth, it functions in environments where bandwidth is scarce, and traditional agricultural extension workers are stretched too thin to reach every field. The inputs are vastly diverse. One ping might be a request to identify a localized crop disease in Kenya, while another flags a land use anomaly in the American Midwest. By removing the friction of a complex user interface, the system generates a high-frequency stream of ground truth data points that institutions can use to fill the gaps between satellite passes. For this data stream to be utilized by federal agencies or international organizations, it cannot resemble a social media database. It must be private by design. Before any record is stored, the incoming data passes through a SHA-256 cryptographic hash. This irreversibly strips away all personally identifiable information, leaving behind only the raw environmental signal. The backend then snaps these individual coordinates into a standardized county-level FIPS grid. This deliberate abstraction prevents the tracking of a specific farmer or an individual parcel of land, while preserving the exact regional resolution required for large-scale analysis. It is this specific cryptographic step that allows private, local conversations to scale into a secure intelligence asset for government and federal use. With privacy secured, the system begins stacking these queries over time into 3 distinct analytical layers. The seasonal layer captures immediate phenological shifts. If queries about spring planting emerge 2 weeks earlier than they did the previous year in a specific county, the system logs a fingerprint of local climate adaptation in progress. The annual layer tracks slower degradation. It maps regional trends in soil organic matter depletion or creeping salinity across multiple harvest cycles. Finally, the perpetual layer acts as a living correlation matrix, drawing lines between a sudden drop in water quality and a shift in crop selection years down the line. Finding these non-obvious causal relationships usually requires dedicated, grant-funded scientific research. Here, they emerge as a byproduct of routine use. By structuring time, LeafEngines converts transient daily chat logs into a permanent, compounding environmental record. This graph demonstrates how that historical record enables anomaly detection. When a cluster of queries deviates from the established baseline and crosses a statistical threshold, it triggers an automated alert. If dozens of users in a historically stable region suddenly ask about drought-tolerant crops, that anomaly is visible weeks before physical satellites confirm a drop in soil moisture. As the data density in a region matures, the forecasting models evolve from basic linear regression into complex Bayesian hierarchical models, continually refining their accuracy against the incoming stream. For agencies like FEMA or state conservation districts, these models provide a critical lead time. They offer the ability to stage resources and initiate responses based on localized distress signals. The network uses the mathematical weight of localized text queries to extract tomorrow's environmental crises from today's data. Every query run through the system increases its predictive power, creating a structural data moat where the value of the information is non-rivalrous. A farmer in Iowa asking about field drainage mathematically improves the baseline intelligence available to a grower in Punjab 3 years later. The more it is used, the more accurate the underlying correlation matrix becomes. This aggregated intelligence feeds directly into private sector infrastructure. Insurers use it to refine parametric crop models, while carbon market verifiers use the regional query patterns to validate baseline conditions for offset projects. In the public sector, tracking query spikes in historically unmonitored regions provides critical intelligence for famine early warning systems and international food security analysis. The users interacting with the chatbot see a helpful digital assistant. The institutions plugging into the backend see a continuous, privacy-preserving repository of global ground truth. Viewed on a decadal timeline, LeafEngines serves as a primary historical record, documenting the evolution of environmental concern alongside the conditions themselves. The system turns human attention and curiosity into the sensors of a planetary network. Over 15 or 20 years, this corpus becomes a primary layer of training data for Earth system models and international climate assessments, documenting exactly how populations reacted as their local environments changed. Unlike the point-in-time snapshots captured by institutional satellites, this data is alive. It is continuous, crowdsourced, and anchored in the experience of the people managing the land. By democratizing the ingestion of environmental data at zero friction, LeafEngines is building an intelligence layer that scales in resolution and predictive power with every question asked.